speaker, Dr. Joydwip Singh from IISER Kolkata. So he shall be talking on bilinear Bochner means associated to the sub-Laplacians on Métivier groups and Grushin operators. With this, I would like to invite him to deliver his talk. I also request all the participants to mute their microphone. Over to you, Joydwip.
Okay, thank you, Munada, for the invitation and giving me the opportunity to present my work here. So today I will, as everyone can see, today I will talk about the bilinear Bochner-Riesz means for the sub-Laplacian on Métivier groups, also on for the Grushin operators. So this is a joint work with my supervisor Sayan Bagchi and Nurul Molla. So let us start. So before that, so let us give some overview of the talk. So first I will discuss about the linear Bochner-Riesz operator on Euclidean spaces. Then I move to the bilinear Bochner-Riesz operator on again Euclidean spaces, and I give some history and details about bilinear Bochner-Riesz operator. After that, I will show how one can define the Bochner-Riesz operator outside the Euclidean spaces. Then I go back to the bilinear Bochner-Riesz operator and linear Bochner-Riesz operator on the setting of Métivier groups. And at last, I will talk about the Bochner-Riesz means for the Grushin operators. Again, bilinear and linear both. So for that, first, let us define the Bochner-Riesz operator on Euclidean space. So that we denote it by S alpha, and which is a Bochner-Riesz operator of order alpha bigger than 0, which is defined by this integral, which is integral over Rn 1 minus mod xi squared to the power alpha f at xi e to the power 2 pi I x dot xi. Where first bracket r plus means it is maximum of r comma 0. Means that if mod xi square is bigger than 1, then we set this multiplier to be 0. And if mod xi square less than 1, this is 1 minus mod xi squared to the power alpha. And initially we defined it for Schwarzschild function to make the integral well defined. And one can see that basically alpha equals to 0, this is the well-known partial integral operator in Fourier integral, right? So basically this is related to the Fourier convergence or boundedness of the Fourier series or Fourier integral. And one can also see that this is a basically Fourier means multiplier operator. If we take the Fourier transform of S alpha, then in the Fourier transform side, it is the multiplication by this multiplier 1 minus mod xi squared to the power alpha. Okay, so as I mentioned that this Bochner-Riesz means can be seen as a attempt to justify the Fourier inversion, because as alpha equals to 0, this is the basically the Fourier inversion formula. And so the Bochner-Riesz conjecture generally talks about the finding the optimal range of alpha for which the operator S alpha is bounded on LP of Rn. So we want to talk about when this operator is bounded on LP of Rn. So for the case when n equals to 1 and alpha equals to 0, as we have seen that this operator is the partial integral means partial integral operator or partial sum, then it is known that S0 is bounded on LP for P strictly lying between 1 and infinity. Okay, so and for P equals to 1, one can see that this does not converge in L1. Now one can easily see that this S alpha is a convolution operator, but the convolution kernel is given by this one, where in the numerator this is Jn by 2 plus alpha is the Bessel function of order n by 2 plus alpha. And using the properties of Bessel function, one can see that when this kernel will be integral by the Young's convolution equality, S alpha will be bounded on all LP, right? So from that integrability of this K alpha, one can get that if alpha bigger than n minus 1 by 2, then this means kernel of this Bochner-Riesz operator is integrable. And therefore the S alpha is bounded on all LP for P lying between 1 and infinity. So this is true for any n bigger than 1. And now for n bigger than 2, when alpha equals to 0, so this is basically the characteristic function of the unit ball. So that's why it's called sometimes S0 to be the ball multiplier operator. And the famous result of Pepperman showed that this S alpha when alpha equals to 0 is unbounded on all LP except P equals to 2. So therefore one cannot, therefore one look for the boundedness for alpha bigger than 0 and when alpha is less than n minus 1 by 2. And n minus 1 by 2 is sometimes called the critical index for the boundedness of Bochner-Riesz operator. So therefore, we are interested for the case when alpha lying between this range. Then again, from this kernel expression and properties of Bessel function implies that S alpha is unbounded on LP if P and alpha satisfies this relation. So therefore, naturally one conjecture that complement of this T condition, Bochner-Riesz operator should be bounded. So this is the Bochner-Riesz conjecture. It states that if P lying between 1 and infinity and P not equals to 2, then the Bochner-Riesz operator is bounded on LP of Rn if and only alpha bigger than alpha P, where alpha P is the number maximum of these two quantity, n into 1 by P minus half, comma 0. Okay, so we are, so this is the Bochner-Riesz conjecture for Rn. And when n equals to 2, it is known that Bochner-Riesz conjecture holds to be true, and it was shown by Carlson and Solin in 1972. But for n bigger than true, this Bochner-Riesz conjecture still remains open, and only partial results are known, but not in general it's true, means it's not known. So the first case when maximum of P and P dash is bigger than this number 2 into n plus 1 by n minus 1, then first Pfefferman-Einstein shows that how one can relate the Bochner-Riesz operator to the restriction theorem on a sphere. One can relate it to the L2 restriction theorem on a sphere, and from that the sharp L2 restriction theorem for a sphere is known there, which is also called the Stein-Thomas. From that one can deduce that S alpha is bounded on LP if P maximum of P and P dash is bigger than. So therefore Bochner-Riesz conjecture holds if P and P dash satisfy this condition. And this exponent sometimes also called the Stein-Thomas exponent. And after that, in R3, Tau and Vargas in 2000 improved the result for the n equals to 3. So they showed that Bochner-Riesz conjecture is true if P is bigger than this number, 4 minus 2y7. And one can check that when n equals to 3, this number means bigger than this number. So therefore, this improves the previous means known bound for Bochner-Riesz. And when n bigger than 3, in 2004, Sangyugli proved that Bochner-Riesz conjecture is true if maximum P and P dash is bigger than this number, 2 plus 4 by n. Again, for n bigger than 3, this improves the previous known bound via Stein-Thomas. So n bigger than 3, this is the still.
So is this result is better
yes.
for this Tau and Vargas result for n equal to 3?
Yeah, it's better for n equals to 3 also.
Okay.
Yeah. And so for n bigger than 3, this is the best known result. And for n bigger than 5, Burgen and Guth, and in 2011, they showed that if maximum of P and P dash is bigger than this number, 2 plus 12 by 4n minus 3 minus k, and if n congruent k mod 3 or k is minus 1, 0, and 1, then this again improves the results for n bigger than 3 also, this result of Sangyugli and also the Pfefferman-Einstein result. So this is the best known result till today's date for n bigger than 5. So one can see this via this picture. So this is in the x-axis I plotted 1 by P and y-axis alpha. Then the red region where it is known that Bochner is unbounded on operator is unbounded on LP. And for alpha bigger than n minus 1 by 2, this is the gray region. It follows from the integrability, which I have shown that Bochner-Riesz kernel is integrable, then is bounded. And the blue region, which follows from the Stein-Thomas bound by the Pfefferman and Stein. And for n equals to 2, it's known for every region outside the red region. But for n bigger than 3, Sangyugli has improved this result Stein-Thomas in the green region. And Burgen and Guth for n bigger than 5 improved again in the orange region. So n bigger than 5, this white region is still open. And n bigger than 3 is this orange union white is still open. And this exponent, this is the Stein-Thomas exponent, n plus 3 by 2 into n plus 2 into by 2 into n plus 1. Okay. Next, I move to the bilinear Bochner-Riesz operator. So like Bochner-Riesz operator in Rn, one can define the bilinear Bochner-Riesz operator similarly, which we denote it by B alpha on Rn of order r bigger than 0, which is defined by this integral over r at 2n. It's 1 minus mod j square minus mod eta square to the power alpha f at j g at j e to the power 2 pi I x j plus eta dj d eta. Again, we initially defined it for Schwarz class functions. And one can see that this bilinear Bochner-Riesz operator is also related to the convergence of Fourier series for product of two functions, f and g. So, like in the linear case, okay, so boundedness of one wants to find the optimal range of alpha for which the bilinear Bochner-Riesz operator, in this case, is bounded from LP1 cross LP2 to LP. Where P1, P2, P satisfies this Hölder relation, 1 by P1 plus 1 by P2 equals to 1 by P, and P1 and P2 should be lying between 1 and infinity. So note that here when P1 and P2 lying between 1 and infinity, P can no longer, means P may be less than 1. So therefore P can be bigger than 1 and also less than 1, but P bigger than half. So the P less than half situation we call, because the LP is no longer Banach space, so we call it non-Banach situation when P is less than 1.
Actually, I have a small question. Why you take this condition 1 by P is equal to 1 by P1
this
plus
is
1 by
basically the Hölder relation. For if one takes for the product of two functions, then one can show that if one assume the Hölder relation, then this is bounded. So this is the natural condition for bilinear.
It's a natural thing.
Yeah, because for product of two functions, when this will be bounded, one can think of, because this is the whole bounded if one satisfies.
Integration of the two function, right?
Yeah, product. Yes.
Then okay, so till then it doesn't convince me. Okay, anyway, so probably.
Yeah, means
I understand that. Okay, if you take this function f and g, and with this condition, probably product of f and g will be inside LP.
Yeah, right. So that's why one naturally takes, and also sometimes someone also takes the bigger than condition or less than some kind of, because this is the endpoint situation for some inequality case. So that will also follow from this one.
Okay.
Okay. So like the linear Bochner-Riesz case, using from the linear Bochner-Riesz, one can also deduce the kernel of the bilinear Bochner-Riesz operator. So this is the bilinear Bochner-Riesz kernel. One can see that this is the basically linear Bochner-Riesz kernel when you view it on R2n. So then it will be of this form j of n plus alpha 2 pi into mod of y comma z by mod of y comma z to the power n plus alpha. So then again, if one can check that using the properties of Bessel function, that k alpha satisfies this bound, is 1 by 1 plus mod y to the power n plus alpha plus half by 2 and 1 by mod 1 plus z to the power similar. Then if one use this bound in the expression of bilinear Bochner-Riesz, and one can see that when this is integrable, means 1 plus mod y and also 1 plus mod z. So then using the Hölder relation and the Young's convolution equality, one can see that bilinear Bochner-Riesz is bounded from LP1 cross LP2 to LP. So from that one can deduce that if alpha bigger than n minus half, then the B alpha is bounded from LP1 cross LP2 to LP. If P1 and P2 satisfies between 1 and infinity and satisfy the Hölder relation. So this we got from the integrability. And also when n equals to 1, the basically Bochner-Riesz bilinear Bochner-Riesz was almost solved for the case when P1, P2 and P lying between 1 and infinity. So here we assume P is in the Banach case. For some non-Banach case, it was shown some result in Joydwip and Srivastava in 2022. So there they proved for boundedness for maximal Bochner-Riesz, but this will imply also the normal Bochner-Riesz operator for non-Banach region also. And n bigger than or equals to 2, then it is shown by Grafakos and Distel that B alpha is unbounded when alpha equals to 0 if exactly one of P1, P2 and P dash is less than 2. Basically, they have modified the argument of Pfefferman for the ball multiplier operator, and then show that B alpha when alpha equals to 0 is unbounded. If P1, P2, P dash satisfy this.
Actually, can you repeat this n is equal to 1 case?
Yeah,
the
means,
Graphacus and
Graphacus, Lee and Barnicot, they have almost completely solved for the Banach case, when means P lying between 1 and infinity.
Okay.
And non-Banach case they have not done, but later Joseph and Srivastava have done some boundedness for maximal Bochner-Riesz,
Okay.
and this implies some condition result for n equals to 1 for Bochner-Riesz operator.
And what about this Barnicot and tal?
Yeah, they have shown, means in Graphacus they have not get the full range, or Barnicot for Banach case they have full range, they have got the result.
Okay. So a little bit of thing. Anyway.
And for n bigger than 2, this is known to be unbounded if exactly one of P1, P2, P dash is less than 2. So therefore one look for the alpha and alpha bigger than 0. This was first studied by Barnicot et al. In 2015 for n bigger than 2. So they have proved that B alpha, this bilinear Bochner-Riesz operator, is bounded from L2 cross L2 to L1 for alpha bigger than 0. And this result was sharp. Also, they have proved that for B alpha is bounded from L2 cross L infinity to L2 for alpha bigger than n minus 1 by 2. And from L1 cross L infinity to L1 for alpha bigger than n by 2. And also from L1 cross L1 to L half, basically this is the non-Banach case. For alpha bigger than n minus half, this is also sharp. Basically this also follows from the integrability as we have shown previously. And B alpha is bounded from L infinity cross L infinity to L infinity for alpha bigger than n minus half. So in picture we can see this. For the Banach triangle case, basically these are the result. So in the x-axis if we put 1 by P1 and y-axis if we put 1 by P2, then this is the case when 1 by P1 and 1 by P2 are lying between 1 and infinity. So this point, this is the 1 infinity 1. So they have proved for alpha bigger than n by 2, this is bounded. And also by changing f and g, one naturally got infinity 1, infinity. And for this is the 2 infinity 2 case, they have got for alpha bigger than n minus 1 by 2. And 2 to 1 case, they have got alpha bigger than 0. And from 2 infinity 2 and for alpha infinity 2 to, this is the basically interchanging f and g. And this is the case infinity, 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 alpha bigger than n minus half. So then interpolating all these points, one gets the entire black region. And this is the 1 half case, non-Banach case they have got. This is follows from the integrability. And these two results are sharp, 2 to 1 and 1 half. These two are known to be sharp. So if one interpolate, one gets these results, means in region 1, 2, 3, and 3. So this is the region get if one interpolates. So for alpha bigger than this number in the region 1, alpha bigger than this number for the region 2. And just interchanging P1 and P2 region, this 2 region one gets. And the last one follows from the integrability of the Bochner bilinear kernel. Okay, now after that there is an improvement for the Banach triangle case, means not entire region, for when P1, P2 lying between 2 and infinity. These were done by Jiang, Sangyuk Lee and Vargas in 2018. Basically they introduce a new decomposition and they relate the bilinear Bochner-Riesz with some linear Bochner-Riesz operator, square function of the Bochner-Riesz operator, and from that they deduce the improved result of Barnicot. And for the non-Banach triangle case, Liu and Wang in 2019 also improved the result of Barnicot. So they proved that B alpha, basically, except this point, it was unknown, right? 1 to 2 by 3 in the non-Banach. Because if one knows at this point, then one can interpolate with the previously known results and then get the non-Banach case. So therefore, they proved that B alpha is bounded from L1 cross L2 to L2 by 3 for alpha bigger than n by 2. And then interpolating, one gets the entire non-Banach range, means 4, 4 and 5, 5. So this is the interpolation ranges, what they have got. Liu and Wang in 2020, region 4 and 5. So up to that, I have talked about on our Euclidean case. Now beyond the Euclidean setting, so how to define the Bochner-Riesz means. So one can see that Bochner-Riesz operator is basically the radial Fourier multiplier of the Laplacians. Basically from the spectral theorem, one can see that this is the basically 1 minus Laplacian to the power alpha is the radial Fourier multiplier for Laplacian, where delta is the Laplacian and bracket of S plus is maximum of S comma 0. Where because the Laplacian is this non-negative self-adjoint operator, then one naturally wants to replace this Laplacian by any non-negative self-adjoint operator. So therefore, we define the Bochner-Riesz operator for any non-negative self-adjoint operator by the spectral theorem of L by this 1 minus L to the power alpha of F. So this is the definition for Bochner-Riesz operator for any non-negative self-adjoint operator. So now we want to talk about the Bochner-Riesz operator for Métivier groups. So before that, let us give some basic details of Métivier groups. So let G be a two-step stratified Lie group. This is connected, simply connected, two-step nilpotent Lie group. And with Lie algebra, there is a decomposition. G is G1 direction G2, such that Lie bracket of G1 and G1 is G2, and G with G2 is 0. So this is G1 sometimes called the first layer, and G2 is called the second layer. So let D1 to be the dimension of G1 and D2 be the dimension of G2. Then the homogeneous dimension is defined to be the summation of 1 into G1, 2 into dimension of G2, like that. So basically the Q is, we got D1 plus 2D2, which is called the homogeneous dimension of G. And Euclidean topological dimension is basically the dimension of G1 plus dimension of G2. So D1 plus D2. So in the latter, we will always Q means this is the homogeneous dimension and D is the topological dimension. So one can see that Q is strictly bigger than topological dimension. So now let x1, x2 up to x d1 be the basis of G1 and t1 up to t d2 is the basis of G2. Then for any mu, which is G2, let G2 be the dual of G2 star with the dual of G2. Then for any mu in G2 star, one can define the skew symmetric bilinear form omega mu, which is defined from G1 cross G1 to R, which is defined by omega mu of x x dash, mu of Lie bracket of x x dash, because Lie bracket of G1 and G1 is G2, so it is well defined. Now we call G to be Métivier group if this skew symmetric bilinear form is non-degenerate for all non-zero mu in G2 star. Means that if omega mu of x x dash is 0 for all x dash in G1, then x should be 0. So then we call G to be the Métivier group. And now we can also define, give the inner product on G such that this basis x1 up to x d1 and t1 up to t d2 should be orthonormal basis of G. And this inner product also induces a norm on G2 star, which we call denoted by mod. Then for any mu in G2 star, there is a skew symmetric endomorphism J mu, which is defined from G1.
So how is it a positive definite or something? How it can induce the norm? Can you go back to the previous slide?
Yeah.
So you are saying that, okay, this W mu is really induces norm or this inner product?
This inner product.
Oh, sorry, I can't took it. Okay, sorry. Yeah.
And so for any mu in G2 star, there is a skew symmetric endomorphism J mu on G1 such that omega mu x x dash will be J mu x and inner product of J mu x and x dash. So then one can see that G is Métivier group if and only if J mu is invertible for all non-zero mu in G2 star. And G is called to be the Heisenberg type group if J mu square equals to minus mod mu square times identity on G1 for all mu in G2 star. So therefore, these two means by definition, one can see that Heisenberg type group is contained in the class of Métivier groups. In fact, one can show that this containment is strict Basically, this was, one can find example in Molla and Seeger in 2004, that Métivier class of Métivier group is strictly larger than the class of Heisenberg type group. Now, corresponding the basis of the first layer, x1 up to xd1, one can define the sub-Laplacian, which is denoted by L, which is a second order left invariant differential operator, which is defined to be the minus of sum of squares of the xi squares. And one can show that L is a positive and essentially self-adjoint operator on L2 of G. Now, because G is a nilpotent group, so the exponential map from the Lie algebra to G is a global diffeomorphism. So therefore, the Haar measure on G is basically the Lebesgue measure on the G. And okay, so now I am talking about the Bochner, means boundedness of Bochner-Riesz operators on outside the Euclidean setup. So for the Hermite operator, Thangabelu in 1891, they proved for Hermite operator, they give boundedness for Hermite operators. And for sub-Laplacian on the Heisenberg group, in 1990, Thangabelu also studied this. And for the sub-Laplacian on any two-step stratified Lie group, Christ in 1991, so he basically proved that Millin-Horman type LP multiply theorem, and from that he deduced that if alpha bigger than q minus 1 by 2, where q is the homogeneous dimension, then the Bochner-Riesz operator is bounded on LP for p lying between 1 and infinity. So at that time it was not known that alpha, this smoothness parameter, this is sharp or not. Later in 1994, Muller-Einstein, and in 1993, Heavis, independently they shows that for the case of Heisenberg type group, that this smoothness parameter is not sharp. Means one can replace this q minus 1 by 2 with d minus 1 by 2, where d is the topological dimension. So, and this results is sharp. So therefore, for sub-Laplacian, from replacing the smoothness parameter by homogeneous to topological is a very interesting problem, and many authors after that started to work on this. For the Martini in 2015 shows that for the Heisenberg writer case, if alpha bigger than d minus 1 by 2, then again Bochner-Riesz operator is bounded on LP. For Lie groups of polynomial growth, again Martini in 2012. For two-step stratified Lie group, but for small dimensions, Martini and Molla in 2014 again give the same result. But here so that they have only for in general any two-step stratified Lie group, it is still unknown whether this d minus 1 by 2, where d is the topological dimension, is enough to guarantee the boundedness for Bochner-Riesz operator. For particular cases, it is not known, but for in general two-step, it's unknown. Now I want to talk about define the Bochner-Riesz operator on Métivier case. For that, let us define the Fourier transform. So for f being L1 of G and mu in G2 star, we define the Fourier transform of f for the over the central variable f mu of x. It is the integral of G2 f of x u e to the power I mu comma u du. And also we need the eigenfunction for this sub-Laplacian. For that, let us define the BR scale Laguerre functions. So for n in non-zero natural number and b in, this is a vector in 0 infinity to power n, and rk also the vectors in n to the power n. Then this is the BR scale Laguerre functions. And it is the tensor product of this phi k1 b1 r up to phi kn bn rn. Or phi k lambda m is the lambda scale Laguerre function, which is given by this. And where lk m minus 1 is the kth Laguerre polynomial of type m minus 1. And for we also define the mu twisted convolution for phi and psi in the Schwarzschild function in G1. So this is defined by this is the just convolution with the extra twist is here e to the power I by 2 omega mu of x dash. So this is the mu twisted convolution. Now we define the Bochner-Riesz means on the Métivier groups, which is denoted by S alpha of L which is defined by this integral over G2R star summation k to the n to the power n 1 minus lambda k mu to the power alpha f mu twisted convolution with phi k b mu r mu inverse evaluated at x and e to the power I mu u d mu, where n is the natural number and r is the vector in n minus 0 to the power n. B mu is also a vector in 0 infinity to the power n. And G2R is a Zariski open subset of G2 star. And this is the eigenvalue for the sub-Laplacian lambda k mu, which is summation of n equals to 1 to n, 2kn plus rn, bn mu. And the functions, this bn mu are the functions from the G2 star. They are of homogeneous of degree 1. And they are continuous on G2 star and real analytic on this Zariski open set. Means they are basically smooth. And they are positive for all mu non-zero mu's. And the function R mu is also function from G2 star, which are orthogonal matrices on RD1. They are Borel measurable functions and are homogeneous of degree 0. So one can see that in the case of Heisenberg-Reiter group, n is basically 1, and this bn mu, this vector is basically mod mu. So this eigenvalue will be of the form 2k plus d1 by 2 into mod mu. So for general n, this is the Métivier group, and for Heisenberg-Reiter, n equals to 1. Means Heisenberg type groups. This is it, sorry. N equals to 1 case is the Heisenberg type case. Now we want to talk about the boundedness of these Bochner-Riesz means on Métivier groups. So in 2012, Martini showed that if alpha bigger than d minus 1 by 2, where d is the topological dimension, then this Bochner-Riesz multiplier is bounded on LP for p lying between 1 and infinity. And so for the complement case, when alpha lying between 0 and d minus 1 by 2, for the Métivier case, means this is the result for the Euclidean case when Stein-Thomas ranges. So this we define the Stein-Thomas exponent. So we have defined it for the point except these 2 points, 8,6 and 8,7. And for these 2 points, I have defined these 2 exponents. Then Nidrop in 2025, he has shown that if p lying between this range and alpha bigger than this number, d into 1 minus p minus half, then the Bochner-Riesz operator is bounded on LPG. So here that we need to exclude these 2 points because for the Métivier case, we have seen that there is a Zariski open set. So in the complement of Zariski open set, there might have the singularity for the functions b mu. So in the Métivier case, because this proof depends on the restriction theorem on Métivier groups, but for restriction theorem is not known, but a weaker version he has proved, and from that he has deduced this result. So therefore we need this restriction, But in the case of Heisenberg type, one can remove this restriction for these 2 points. Then if p lying between 1 and 2 into d2 plus 1 by d2 plus 3, this is the Stein-Thomas exponent, and alpha bigger than d into 1 by p minus half, then the Bochner-Riesz operator is bounded on LP, which Nidrop has proved in 2024 for the Heisenberg type group case. And in fact, from the result of Martini in 2022, so one can show that the above results are sharp. Means this result in terms of the topological dimension, if p lying between this range, then one cannot reduce the range of alpha. So these are the sharp. Okay, now we define the bilinear Bochner-Riesz means for the sub-Laplacian analogously. So for FG and Schwarz-Class functions, we define by this integral. So this is the integral means like the linear case for the two function f and g you have defined. So the one wants to find the optima means alpha p1 p2, which should be in terms of topological dimension. One wants to find such that if alpha bigger than alpha p1 p2, then the bilinear Bochner-Riesz operator is bounded from LP1 cross LP2 to LP, where p1 p2 lying between 1 and infinity, and p1 p2 p should satisfy the Hölder relation. So this is our aim to finding the alpha p1 p2 in terms of the topological dimension. So in this direction, for the sub-Laplacian on Heisenberg group, Liu and Wang in 2019, they proved the boundedness of bilinear Bochner-Riesz, but with homogeneous dimension. And also for the Heisenberg type case, Wang and Wang in 2024, they have again proved the bilinear LP bounded LP1 cross LP2 to LP boundedness of bilinear Bochner-Riesz. So these are their ranges. So all this they have get with respect to the homogeneous dimension Q. Like in the linear means for the Bochner-Riesz, one can expect that this should be true for the in terms of the topological dimension. One can expect. So basically, they have get the similar result as Euclidean, but in terms of the homogeneous dimension. Except at this point in Euclidean, it is n minus half, but they have got it q. So after interpolation, the results look like something like this, where the this smoothness parameter in terms of the homogeneous dimension. Now, for the Métivier case, we have proved the following result for the boundedness. So the bilinear Bochner-Riesz operator is bounded from L2 cross L2 to L1 if alpha bigger than 0. And it's from L2 cross L infinity to L2 if alpha bigger than d by 2, where d is the topological dimension. And L infinity cross L infinity to L infinity if alpha bigger than d minus half, again d is the topological dimension. From L1 cross L1 to L half, this is the non-Banach ranges for alpha bigger than d plus 1. And L1 cross L2 to L2 by 3, this is again non-Banach case, and alpha bigger than d plus 1 by 2. And but for the L1 cross L infinity to L1, we have only got the homogeneous dimension. So in the picture, if one plots the 1 by P1 in the x-axis, 1 by P2 in the y-axis, then these are the results we have got. At 1 half, it is d plus 1, alpha bigger than. At 1 to 2 by 3, it's d plus 1 by 2. And by interchanging f and g, again, it's same d plus 1 by 2. For 2 to 1, it's alpha bigger than 0. And 2 infinity 2, it's d by 2. Again, infinity to infinity is d by 2. And infinity, it's d minus half. But 1 infinity 1, we only get in terms of the homogeneous dimension. So if one interpolate, one get this result after interpolation. So in the region 1, we entirely get in terms of the topological dimension, because here we got everything in terms of the topological dimension. In region 3, both mixture of topological and Euclidean. In region 4 also mixture of topological and homogeneous. And region 5, it's d1 plus d plus 1 into 1 by p minus half. One can improve these results if one gives some restriction on f and g. So this is the improvement we got, because for L1 infinity 1, we get only homogeneous previously. So if one assume that Fourier transform of G is supported f from 0, means on a fixed number, then one can improve the results. Means then it will get in terms of the topological dimension, alpha bigger than d by 2. Also one can, because infinity 1 infinity also same result. And 1 to 2 by 3 Banach case also improve, means we can improve the plus half, means d plus half previously we got, here we got d by 2. If one assume that support of Fourier transform of support of G is outside 0. And also for the L1 cross L1 to L half, if one assume both Fourier transform of f and g are both supported from 0. Then again we can improve, because previously we get d plus 1, now here we got d. So this is the improvement under the assumption on the support of the Fourier transform of f and g. So this is the picture where here we get alpha bigger than d in terms of topological dimension, alpha bigger than d by 2, d by 2. This we got alpha bigger than d by 2 under the assumption. And others in terms of the topological dimension. Now we move to the Bochner-Riesz means for the Grushin operators. So let us define the Grushin operator on Rd. So for any point of Rd, we denote it by x dash comma x double dash, which is the point from Rd1 cross Rd2. So then the Grushin operator is defining the minus of Laplacian of the x dash variable minus x dash square mod square into Laplacian on the x double dash variable. So this is, one can see that this is a positive and essentially self-adjoint operator and on L2 of Rd. But this operator is not elliptic, because when x dash equals to 0, one can there is a problem. So one can show that, but this is a hypoelliptic operator because one can write this is a sum of squares of the vector fields. So then by Hormander's theorem, this L is a hypoelliptic operator. And corresponding to this, basically, there is a Carnot-Cartesian distance for any xy, and this distance is again equivalent to this expression, which is given by this or any 2 point x and y in Rd. Now, corresponding to this distance, we can define the balls. So this is the all such point in Rd, such that rho xy in less than r. This is ball centered at x and radius r. Then if one computes the volume of this ball, then it will look like r to the power d1 plus d2 into maximum of r and mod x dash to the power d2. So note that here the ball not only depends on the radius, but also it's depend on the point. So therefore, this makes the analysis for Grushin operator more challenging. And if one scales this radius by some positive number eta, then it will satisfy this relation 1 plus mod eta to the power q into measure of the ball b of x comma r, where q is d1 plus 2 d2. And because of that, this q d1 plus 2 d2 is called the homogeneous dimension of Rd, and d1 plus d2 is called the topological dimension of Rd. Now we can similarly define the, using the spectral theorem for the Grushin operator, we can define the Bochner-Riesz operator via this. This is the integral of our Rd, summation k equals to 0 to infinity 1 minus 2k plus d1 mod lambda to the power alpha, pk lambda f lambda e to the power I lambda dot x double dash d lambda, where f lambda is the Fourier transform in the x double prime variable, f of x double prime e to the power minus I lambda x double prime. And pk lambda is the projection of G onto the kth eigenspace, where phi mu lambda are the, for lambda not equals to 0, are the scaled Hermite functions on Rd. So we again want to talk about the boundedness of this Bochner-Riesz operator for Grushin. Then for the range for P strictly lying between 1 and infinity, Martin-Ishikawa proved that if alpha bigger than this number, maximum of d1 plus d2 and 2 d2 minus 1 by 2, then this S alpha is bounded on LP. So note that here, this is not entirely in terms of the topological dimension, but if one takes d1 bigger than d2, this is the topological dimension. So for d1 bigger than d2 case, they get the in terms of topological dimension. Later, in 2014, Martini and Molla proved for all d1, d2 in terms of the topological dimension. So they have improved the result of Martin-Ishikawa for alpha bigger than d minus 1 by 2. And for the case when alpha is less than d minus 1 by 2, and when p is lying between this is the basically Stein-Thomas exponent. This comes from the both Stein-Thomas ranges. 2d1 p should be minimum of these two number, and alpha bigger than maximum of d1 plus d2 2d2 into 1 by p minus half. Then Chen Wawaj in 2000 proved the boundedness for S alpha for alpha less than d minus 1 by 2. So again here, if d1 bigger than d2, only we get the Euclidean, but other than we get bigger than the topological dimension. So later in 2022, Nidrov proved for all d1, d2 in terms of the topological dimension. He proved that it alpha bigger than d into 1 by p minus half, then the S alpha is bounded, or S alpha is bounded if p satisfies this condition. And in view of the result of Martini of 2022, the above results in terms of d, means the topological dimension, this and this, they are sharp. Now we move to the bilinear Bochner-Riesz means for the Grushin operator. So we can similarly define the bilinear Bochner-Riesz operator via this, like the linear case. And again, we want to talk about the LP1 cross LP2 to LP boundedness, where P1, P2 satisfy the Hölder condition. So this is the result we got for the bilinear Bochner-Riesz for Grushin operator. Again, L2 cross L2 to L1 alpha bigger than 0. L2 L infinity to L2 alpha bigger than d by 2, and infinity for alpha bigger than d minus half, and 1 half, this is the non-monad case, alpha bigger than d plus 1, 1 to 2 by 3 alpha bigger than d plus 1 by 2, but 1 infinity 1 we again get the homogeneous. And one interesting fact that for Grushin operator in the non-Banach case, here d plus 1 by 2 and d plus, this can be improved for the case d1 bigger than d2 for the Grushin operator. So first let us, so this we have got for any d1, d2, this is the result we have got for the Grushin operator. All these are in terms of the Euclidean except this at point 1 and 1 infinity 1. Now interpolation we get this result. This is the result we have got. And so for the case d1 bigger than d2, we can improve the result. And so b alpha is bounded from L1 cross L1 to L half for alpha bigger than d and not d plus 1. So this is the improvement. And for b alpha is bounded from L1 cross L2 to L2 by 3 for alpha bigger than d by 2. So these are the result we got for d1 bigger than d2, improvement these three. And other are the Euclidean dimension we got previously. But here again, these are the, we got only the homogeneous dimension at 1 infinity 1. And if one assume the same condition on the support of the Fourier transform of f and g, then one can improve the results. Meaning one get L1 cross L infinity to L1 with in terms of the topological dimension. Again, the same result as Métivier. So one can improve if one assume the support condition of f and g. So this is the pictures when we get the everything in terms of topological dimension, but with the extra assumption that support of f and g are the supported out from the 0. Okay, thank you.
Uno?
Hello.
Yes, yes. Hello, are you able to hear me?
Yeah.
Oh, yeah. Okay, so are there any question from the audience?
Okay, Joydip.
Yeah.
So the result of Martini for Bochner-Riesz mean in Heisenberg group. So he has proved. Yeah, the slide number I
think this one.
Yes, here the first thing. So he has proved LP boundedness for all p between 1 and infinity when alpha is bigger than d minus 1 by 2.
Yes.
So in this case, p equals to 1 is not included for alpha strictly bigger than d minus 1 by 2.
Yes, for p, I think for one Bochner-Riesz, yeah, means for this follows from the LP boundaries of the multiplier. So that's why p we have to exclude it. From multiplier, they have deduced it.
It's not from the kernel. Okay.
Yeah, no, yeah.
Yeah. And
The
in
techniques
your
are, yeah.
Yes.
Yeah, please ask. I thought that
okay.
Please ask.
And in your result, that L1 to L half estimate,
Yeah.
I think you have got for after imposing extra conditions on the Fourier support of functions, you are getting up to D.
Yeah.
Yeah. But you expect it to be alpha bigger than D minus half?
Yeah, means for that we need explicit expression for the kernel, but for in this case, we have not got it explicitly.
Yes.
Yeah, so yeah, I think one can expect it should be D minus half.
Okay.
Yeah.
Okay, it was a nice talk.
The thing is, the techniques of proving these results are same or kind of
which one?
The results which analog of results which you have proved in this.
Yeah, means technique means here we need the restriction type estimate, and for the reducing from homogeneous to topological, we need the weighted plancherel techniques that we do not need in the Euclidean case because they are the homogeneous and topological dimensions same. But for the redux, if we want in terms of homogeneous dimension, then the techniques are more or less same. But for the reduction case, we need extra weighted plancherel and sharp restriction type estimates. Means we need extra cutoff something.
Yeah, also, I mean, there are some cases where the multiplication, in Euclidean cases, multiplication of eigenfunction generally can be written as combination of, I mean, linear combination of eigenfunctions. So that property is not there. So we have to find some another proof, and then from that we have to go to the Euclidean dimensions.
Yeah, because for this case, when 2 infinity 2, they have used the result, the product of eigenfunction is again eigenfunctions. But here we cannot use it. So you have to do some different technique.
Okay. So are there any other questions from audiences? So if there are no more questions, let us thank the speaker for a nice talk.
Okay.
Thank you, Joydwip. अच्छा टॉक दिया यार जयदीप। अच्छा ये किया था, मतलब अच्छा प्रिपरेशन अच्छा था तुम्हारा टॉक में। चलो, अरे जयंत कहाँ पे है यार?
और जयंत लिव कर गया शायद। नहीं है।
अरे थोड़ा दिखाओ जयंत, दर्शन दिखाओ तुम्हारा।
हेलो जयंत दा, तो प्रीतम भी था।